In this lesson we're going to look at what is known as the motor effect. And the motor effect can be defined as this, that a current in the presence of a magnetic field will experience a force. So if a current carrying conductor is positioned between the poles of a magnet, then a force will be exerted on that conductor. So a very simple experiment which demonstrates this motor effect is depicted below. What we've got are two conducting supporting rods. Okay, so they're conductors. And so they're supporting a third conducting rod which is free to move. And so normally there'll be a couple of wheels positioned on either end of this conducting rod which will keep it on the track, if you see what I mean. So it's free to move backwards and forwards. And so this conducting rod is positioned between two magnets with opposite poles. So in this case we started off with north-south, north-south. So what we're going to do is we're going to see what happens when the switch is closed and an electric current flows around the circuit in this direction. Okay, coming in this way along the free moving rod in this direction and out this way. Okay, so one important thing is that this rod, which is free to move, is always in electrical contact with these supporting rods. Okay, so none of the rods should be insulated. And also we're using conducting rods because we really want quite a large current flowing through here. Okay, typically 2 to 4 amps. So this force results from the fact that the magnetic field between the two magnets interacts with the magnetic field produced by the current flowing in the conducting rods. And this force will either push the rod to the right or to the left, depending on the direction of the current that's flowing and depending on the poles of the magnet. So let's first of all have a look at the magnetic fields produced by this setup that we've got here to understand what will happen next. So the red magnetic field lines, these concentric circles, represent the magnetic field produced by the current flowing in the conductor. And you remember that as we're viewing it from this side here, that the current is flowing away from us into the screen. Right, so remember our dart from the previous lesson, we can represent that with a cross there. Those are the flights of the dart moving away from us, the current's going into the screen, and that results in a clockwise field direction. Alright, so the magnetic field will be flowing in this direction. Now, how about the magnetic field produced by the magnets? Well, as you remember, magnetic fields always go from north to south, so these will be directed in this direction. And you'll notice that to the left of the conducting rod, the magnetic fields are in the same direction, whereas to the right of the conducting rods, they're opposing each other. So as a result of that, the magnetic field intensity on this side of the rod gets a lot stronger, whereas on the right of the rod, the magnetic field intensity gets a lot weaker. And so the combined effect of the magnetic field pattern, due to the interaction of these two magnetic fields, will look something like this. Okay, so you can clearly see that to the left of the rod the magnetic field is intensified, to the right of the rod it is a lot weaker, and as a result of that a force is exerted on the rod pushing it to the right. Now then, if we do either of the following things, then we will change the direction of that push. So, for example, if we keep the current flowing in the same direction, like that, into the screen, but we swap the poles of the magnet around, this time the field intensity is stronger to the right of the rod and weaker to the left. So the force on the current carrying conductor will act towards the left. Exactly the same reverse effect will occur if I keep the poles of the magnet the same as I had at the start, but instead reverse the sense of direction of the current. So we'll reverse the poles of the battery and the current's flowing in this direction. As a result, the current is now flowing out of the screen. I can represent that with a dot. Current flowing out of the screen, that's the tip of the dart coming towards me. and this results in the same reversal of magnetic field patterns, making the force on the conducting rod act again towards the left, and so causing the rod to move towards the left. So whenever I switch the poles, I'll change the sense of direction of the force that acts on the conducting current, or whenever I change the direction of the current, I will change the direction of the force that acts on that conducting rod. Now, all this looking at magnetic fields and adding them up and subtracting them, as we've been doing here, can get a little bit complicated, can become a bit of a headache. So there's a much easier way of deciding which direction the force acts in this motor effect, and that is known as the left-hand rule, and we'll look at that in the following lesson.